Taking a look at the very front. Shh. Here are some examples below. These are examples of what scale drawings can be for a bus, a scale drawing of a quarter, a scale drawing of the subway lines from Boston, the city of Boston. These are versions that are not considered to be scale drawings. So based off of that, based off of what you're looking at as examples of versus examples of what it is not, what do you think a scale drawing is, David? An accurate, that is exactly what you just said, accurate. It's accurate drawing or an accurate representation of a real item. Okay, so when we're talking about scaling something, it can be something that you're taking and scaling it down, or you could be scaling it up. So we do that often, huh?
Like scaling down up size-wise?
Size-wise, yeah. You guys are talking too much. So when we're talking about scaling an item, a lot of times we scale it up or scale it down. So times that we might scale something up. All right, in 2020, what was the big thing that was all over the news constantly? Coronavirus. And everywhere you looked, they had a picture of what the virus looked like, didn't they? Now, when we're walking around and in the school, are we seeing that virus floating around everywhere with our eye? No, we aren't. But what they're doing, they're magnifying it so that you're seeing what it actually does look like. So anytime that you see a germ or a cell when you're in science, you're looking at a scaled up picture, okay, a scaled up representation. Now we also see something where we are scaling things down. There's a lot of jobs that involve scaling stuff down. So any building that gets built, the first thing that it goes through is a process of creating a small replica of it. Okay, so when we're going and building a school or building a skyscraper or building a home, they first have to develop the plans of what it's going to look like. A scale model is what they'll call it. So it's a smaller replica of what they are planning to make on a bigger scale. If you guys have ever gone to Legoland here in Atlanta, so those of you who've gone, they have that one area that is, they're supposed to have replicated certain portions of Atlanta, right? So they've got like the Coca-Cola building that they've replicated. They've got the stadiums that they've got a replica of. They've got the zoo and the aquarium that they've got replica of. But they're smaller versions of it because obviously they're building it with Legos, but they're trying to make it down to the actual size proportionally. And that's a very key thing to understand, that it is what we call proportional. So like we've talked about before, proportions are equal on a different scale. So right here, I want you guys to write down that what we should notice with a scale drawing, it's a larger or smaller, accurate. So I love the fact, David, that you said accurate. So it's an accurate representation of an actual item. So obviously, like the subway lines are not this small. We couldn't fit it onto a piece of paper. Subway lines are huge, but we have to be able to make it into a map. Maps are common representations for scale drawings. Okay? And again, something to understand, that it's proportional in size. And we have something that's called a scale factor, and we tend to call it the value K. K tends to represent what we call our scale factor. Okay, so what I want you guys to do is take a moment right here, scaling the value F. So this right here is what our original is, and I want you guys to look through these different representations of F, and I want you to think which ones of those can be considered scaled copies of the original. where it stays proportional in its size. Okay, it might have gotten bigger, it might have gotten smaller, but it's proportional in comparison. So take a moment and think of how you might be able to identify which ones are the representations. Okay, right off the bat, who can raise their hand and tell me which ones can we kind of like at least get eliminate? Automatically we can eliminate them. We can definitely cross them off. Give me one of them. Leah? 4. Why can we eliminate 4? It's slanted, right? It doesn't have the exact same look to it. It's different in a sense. What's another one that you think you can automatically go ahead and get rid of? Kai? Huh? Why 6? Very good. She says you can get rid of 6 because the top line and the center line, they match up, whereas in here in the original, they don't match up. The top line's bigger than the center line, so we can immediately get rid of 6. There's one more that we can right away go ahead and cancel out. Lucas? 3. Why do you say that? It looks wonky. Okay, or it's just too stretched out, right? Too elongated, whereas the size, the height didn't change, did it? The height didn't change, but the width of it, the length of it changed. So you can't have a change to one and not to the other. That would distort the image. So we can immediately cross that off. So now we're down to just 4 examples. I will tell you right now, there's one of them that does not belong. Which one still does not belong? Jackie? 5. Okay, so 5 does not belong either. It's not proportional, and we'll show what we mean by proportionality. So the ones that do match up are 1, 2, and 7. So let's take a look at the next page. Go ahead and flip it on over. So 1, 2, and 7 actually do match up, and here's how we can tell. I want you guys right now to count what is the measurement for the vertical line, what is the measurement for the top horizontal line of each of them, and what is the measurement of the shorter horizontal line for each of them, for each of these 4 drawings. Do the original. Zoom in if you need to. Here, I'll zoom in. So based off of what we're seeing here, for our original compared to our different drawings, drawing 1, 2, and 7, the vertical line, what was the vertical line for the original? Fatima?
4.
What about for the drawing 1? What was drawing 1? Montserrat? 6. Drawing 2? Jeremiah? 8. And then drawing 3, Logan? Ooh. Try again. Count it again. 12. Okay, so there's the measurements for our vertical line. What about for our top horizontal line? What was the top horizontal line for the original? Jackie? 2. What about for drawing 1? What was that going to be? Merrick? 3. Drawing 2, what was the top horizontal line going to be? Richard, what did you get for the top horizontal line for drawing 2? 4. Okay, and then for the last one, the top horizontal line, what was that going to be, Hassan? 6. Okay, so you should have gotten 2, 3, 4, and 6. And then we're talking about that center line. That center line, what is that going to be for the first one? For the original, Charlie? I didn't hear. Charlie? For the original, the shorter horizontal line, what was the measurement for the original? It's this line right here, honey, but on the original. What's the measurement for it? 1. Okay, what's the measurement for the drawing number 2? Or, I'm sorry, drawing number 1, Kai? 1.5. Drawing number 2, what was the measurement for it, Fatima? 2. And then drawing number 7, what was the measurement, Lucas? 3. Okay, so here's what we're noticing. For the original started at 4, 2, and 1. and then each of the drawings is going up proportionally by a scale factor, and we're going to talk about that scale factor. But if we were to compare it, 4 over 6 is equal to 2 over 3. 4 over 6 is also going to be equal to 1 over 1.5. 4 over 8 is equal to 2 over 6, and it's equal to 1 over 2. 4 over 12 is equal to 2 over 6, and it's equal to 1 over 3. And all of these scale drawings are equivalent when you create a ratio. 2 or 6 over 8 is the same thing as 4 over 6. You know, they're all going to be able to simplify to the same exact value. Okay? Now, taking a look here at scaling the shape L, what I want you guys to do is, given this original, you are going to identify which one of these is the appropriate scaled drawing. Is it B, C, or D that's the appropriate scale drawing to A? So if A is the original, which one of these is going to be the scaled drawing? Tiffany, which one do you think? C. Okay, C is going to happen to be the scaled version of it. If this one's going by 1, so if we count this out, this is by 1. This measurement here is 1, 2, 3, 4, 5. This original is 1, 2, 3. And then this one's by 1, and this is by 2, and this is by 4, right? So if we are taking a look, the only ones that are going to be proportional to it, this is 2, this is 10, this is 6, this is 2, this is 4, this is 8. What happened in sizes? It what? It doubled in size. Okay. This one, the stretching of it did not change much for the top. Okay, so it did not change everything. All of the measurements are going to have to change in order for the entire shape to have been scaled. So C is the correct one. So let's go ahead and continue. For here, talking about corresponding parts. With corresponding parts, when a part of an original figure matches up with a part of a copy, that's what it means. We call it corresponding. So these could be points, it could be line segments, it could be angles, it could be a distance. They all are supposed to match up with their corresponding values. So for example, if we're talking about point B, so point B is going to correspond with point E on the other shape. That means point C is going to correspond with point F, and point A is going to correspond with point D. That also means that the line segments need to make sure that they match up. So the line segment that goes between A and C needs to correspond with the line segment that goes between D and E, or sorry, D and F. Okay? Also means that the angles, it's not just the point, but the angle inside is going to match up. So whatever the measurement of angle A is, it has to be the same as the measurement for angle D. Okay? They're going to correspond with each other. That means that they're going to be proportional to each other. Yes?
We kind of did this in art class last year.
Yeah, you utilize this a lot in art when you're trying to create
Small picture we drew, and then we drew a
big picture. That's what my extra credit activity project is making a scale drawing of something of your choosing. All right, let's go ahead and flip on over to the next page. So for here, if you'll notice, the measurement that takes us from A to C has a measurement of 6. And then when it corresponds with D to F, it's now gone up to a 12. So what scale factor do you think is happening to go from 6 to 12? What is that scale factor going to be, Zachary? Times 2. So we are multiplying, timesing it by 2. That means that each of these values, if I times 4 by 2, it gives me the 8. If I times 5 by 2, it gives me the 10. So our scale factor in this case is going to be 2. Identify what the scale factor is going to be for the next one. If you're going from 4, 6, 5, now you're going to 6, 9, and 7.5. what is the scale factor that's occurring here? So if we're going from a 6 to a 9, or if we're going from a 4 to a 6, or a 5 to a 7.5, what is the scale factor, Hassan? 1.5. So if we're taking the 6 and we're multiplying it by 1.5, that gives us to the 9. Take the 4 and multiply it by 1.5, that gives us a 6. We take 5 and multiply it by 1.5, that gives us 7.5. So our scale factor in this case is 1.5. Okay? So now based off of that, what I want you to do is taking a look here at our scale triangles. I want you to identify all the scaled copies of triangle O. So triangle O represents our original. Which one of these triangles presented here are going to be copies or scaled triangles of the original? You're going to tell me what the triangle number is, and you're going to tell me what the measurement is that corresponds with the 3, that corresponds with the 4, that corresponds with the side that is a 5, and then what is the scale factor. Go ahead and do this portion on your own. All right, who can raise their hand and tell me what is one of the triangles that is considered to be a scaled version of it? Mario?
E.
E, okay, triangle E is considered to be a scaled triangle. So we'll go ahead and go with E first. If we take a look, what one of the measurements for E matches up with the side 3? What's the measurement? 6. And what matches up with side 4? 8. And what matches up with side 5? 10. What's the scale factor going to be?
2
Timesing it by 2. You're going to times it by 2 for E. That's triangle E. What's another triangle, Fatima? Huh? B. B is technically considered to be a scaled triangle, although it's exactly the same, isn't it? Hasn't changed, right? So 3, 4, and 5. It's just a scale factor of a 1. It has not changed anything about it. It has not scaled up or scaled down. It's just an exact replica. All right, what's another triangle up here that happens to be a scale? Montserrat? Huh? Not F. So F isn't going to be one, because if we take a look at it, does F look the same? Is it set up the same as a right triangle? No, so that's not going to be one of them. Richard? G. G is considered to be one of those, yes. If we take a look at G, 2 matches up with the side that's a 3. The 8/3 is going to match up with the side that's a 4. And the 10/3 is going to match up with the side that is the 5. What's the scale factor then? What's the scale factor? What did we multiply 3 by in order to get a 2? To go from 3 down to the 2, we multiplied it by what? Well, here, let's take a look. You say 2/3? That's okay, so let's take, yeah, that should be it. Yeah, 2/3. I'm so sorry. I should have said yes. I'm so sorry. I didn't think. No. We've got our 2/3. So if we multiply the 3 times 2/3, we're going to get 2. If we multiply 4 times 2/3, we'll get 8/3. If we multiply 5 times 2/3, we'll get 10/3. Okay, there's one more up here that happens to be a scaled one, and that's going to be D. D is also considered to be a scaled. If you look at it, the 3/2, the 2, and the 5/2, what scale factor did we multiply by? To go from 3 to 3/2, what did we multiply by? To go from 4 to 2, what did we multiply by? A half. Multiplied by a half. If you go 3 times a half, you get 3 halves. If you do 4 times a half, you get 2. If you do 5 times a half, you get 5 halves. Okay? Easy way to be able to find your scale drawing. I'll teach it to you in just a moment, okay? All right. We are going to go ahead and quickly, you're going to make your own scale drawing. So based off of this original, so this original has side measurements of 1 and top measurement and bottom measurements of 2. I want you to make another rectangle that has a scale factor of 4. Using these measurements, you're going to do a scale factor of 4 to make your new rectangle. So if we make our new rectangle, we have a 1, a 2, a 1, and a 2. If we're doing a scale factor of 4, that means you're multiplying it by 4. So that means our new measurements should be what? What's our new measurements if we multiply everything by 4? 4 and 8s, right? 4, 8, 4, 8. So that means we're going to start here. I'm going to go ahead and go 1, 2, 3, 4. And then go 1, 2, 3, 4, 5, 6, 7, 8. There's my new rectangle, 4 by 8. Sir? It might not have printed very darkly. I'm sorry. All right, let's go on to the next. All right. So with that information for problem number 2, given this original triangle, 4, 10, and 7, I want you to identify which of these, and there could be more than one, could be considered to be a scale to the original. Yes. What do you mean? Well, it's if you take a look at it, it's always like this is the short side, the medium side, the long side. So it should be short, medium, and long that you're comparing it to. So it might not be written in the same order. So like, well, actually, they all are written in short, medium, and long. Okay, let's take a look at this. So like what I was just saying to him before, when you're comparing, when you're looking, you're going to be comparing what the short side is. You're going to be comparing it with the medium side. And you're going to compare it with the long side. So it needs to make sure that it's going to be consistent throughout when you're looking at your comparison. So if we're looking at problem A, for problem A, our short side compared to the short side for here, if we take the newest one and divide it by the original, that would give us a scale factor of 2. But if we take the medium side of 11 and divide it by 10, that's going to give us a scale factor of 1.1. So right off the bat, that's not going to, or sorry, not the 10, the 7. If we divide it by the 7, that's going to give us a scale factor of 1.57. Okay, so and then we'll have the 14 divided by the 10, and that's going to give us a scale factor of 1.4. So these are not consistent. These scale factors are not consistent, so it is not a scale drawing. So I'm going to go ahead and cross that off. That's not considered to be a scale drawing because of the fact that it's not consistent throughout. Okay, if we take a look at problem B, with problem B, again, take the short side, which is 10, and divide it by the short side of a 4, and that's going to come out to 2.5. If we take the middle side, which is 17.5, and divide it by 7, that's also going to come out to 2.5. And then if we take the 25 and divide it by 10, that's also going to come out to 2.5. So that is considered to be a scale drawing because it's consistent throughout. You get 2.5 every single time that you do the division. Always taking your newest value and dividing it by your oldest value. Okay, if we take a look at C, if I'm taking 6 and dividing it by 4, that's going to come out to 1.5. If I take 9 and divide it by 7, that comes out to like 1.28. So right off the bat, we don't have any consistency here. And then if I take the 11 and divide it by 10, that comes out to 1.1. So these are not consistent. It's not going to be considered to be a scale drawing, so I'm going to cross it off. Okay, if we go to D, problem D, we're going to have 6, again, divided by 4. That's going to come out to 1.5. If I do 10.5 and divide it by 7, that's going to come out to 1.5. And if I do 15 and divide it by the 10, that comes out to 1.5. So it's consistent throughout. That does make it a scale drawing, so I'll circle it. And then for my last one, E, if I take the 8 and divide it by 4, that comes out to a 2. If I take the 14 and divide it by the 7, that comes out to 2. If I take the 20 and divide it by 10, that comes out to 2. So we've got our scale drawings here. So B, D, and E are all considered to be scale drawings. Okay, so scale factors do have an effect on the area of a shape. Your area for a shape is going to be affected, but it's not affected by just the scale factor. It's actually affected in a different way. So I want to see if you guys can figure out what effect actually has in comparison to the scale factor and the area. So taking a look, here's our original. Our original shape is a 2 by 4. So what's the area of this 2 by 4 shape? This 2 by 4 rectangle. What's the area? 8. Okay. The 2 by 4. So 2 by 4 means that we're just going to do 2 times 4, which is equal to 8. Now notice that they said that the scale factor here is a 3. The scale factor happens to be a 3. Okay? So I'm even going to write that down here at the bottom. My scale factor equals a 3, so we're multiplying by 3. But now let's take a look at what happens when I scale these by 3. So if I do 2 times 3, what does that make this measurement? 6. And then 4 times the 3 makes this measurement 12. And what's 6 times 12 for the area? 6 times 12? 72. So even though my scale factor was a 3, did my area get 3 times bigger? No. But my side measurements got 3 times bigger. But what happened to the area? What do you notice? How many times bigger did the area get? 9 times bigger. Okay? So let's take a note of that. That the area got 9 times bigger. Even though the scale factor is 3, it's times 3, the area got 9 times bigger. Now, let me make a little special note down here and see if you can figure out the pattern. If the scale factor is 2, then the area gets 4 times bigger. If the scale factor is, I don't know, sure, 6. If the scale factor is 6, the area will get 36 times bigger.
You multiply the scale factor
by itself, which is another way of saying what? The number to the power of 2. So your scale factor, if you square your scale factor, that will represent the area and how much bigger that it gets. So when we say that it gets 9 times bigger, or 3 squared bigger, okay? In this case, it would be 2 squared bigger, 6 squared bigger. So your scale factor affects your area by squaring your scale factor and multiplying that to the area. Okay, that's the effect that it's going to have. So with that in mind, take a look at the next couple of problems. I want you to identify if this is your shape and your scale factor is a half, then what should the area of your new shape be? You're not going to draw your new shape. You're just going to identify what the area of the new shape should be based off of this original. And then go ahead and answer this question as well. So what was the original area? Who can tell me what the original area was for the shape, Fatima? 80. The original area. So for our original area was going to be 80. If you did 8 times 10, you would get 80. So if we use the scale factor, if we scale factor it, what will that make the new area?
40. Oh, 40.
No. Didn't we just say that you would take the scale factor and raise it to what power? We just said it, didn't we? You would raise it to the second power. So you need to do the same thing here. You're going to take what your original was, the 80, and you're going to multiply it by your scale factor to the second power. That's going to equal 20. So if you guys aren't paying attention, you're going to get that question wrong every single time. If you make a scale copy of the rectangle shown using a scale factor of 4, what is the area of the scale factor going to be? So here, what's the original area? What's 8 times 5? 40. So the original area was 40. If our scale factor is 4, I'm going to multiply this by 4 to the second power. If I do 4 to the second power, which one is that going to be? Do 40 times 4 to the second power. What is it going to give you guys?
640.
Huh?
640.
640. So you should get answer choice C. Answer choice C. It's always going to be your scale factor squared or raised to the second power. Okay? All right, taking a look at some blueprints here. So a builder is using the scale drawing shown to build a house. The figure below shows the blueprint of the family room. So the family room's got a blueprint where it's 5 centimeters by 3 centimeters. Each one of the centimeters represents 3.5 feet. I want to know what is the actual length of and width of the family room. I want to know what is the perimeter, the actual perimeter of the family room, and what is the actual area of the family room. Go ahead and do that now. Okay, if I'm going over this real quickly because I want to make sure we get through these notes before you leave. We've got a length that's going to be our 5 feet. I know that's kind of hard to see, or 5 centimeters. The length that's 5 centimeters, and I'll write that down. That's my length. My width right here, that's my 3 centimeters. So when I'm trying to do the actual length and the actual width, for the actual length, I'm going to take the 5 centimeters and I'm going to multiply it by 3.5 to represent the feet. And that's going to come out to 17.5 feet. So your actual length should be 17.5 feet. When we do the same thing for the width, we're going to take the 3, multiply it by 3.5, and that's going to come out to 10.5 for the feet. So the actual measurements of the family room, 17.5 feet by 10.5 feet. Now when we want to do the perimeter of the actual facility, well, I already know that this is going to be 17.5. I know this is 17.5. I know that this is 10.5 and this is 10.5. So then all I have to do is combine those together for my perimeter. If I do 17.5 plus 17.5 plus the 10.5 plus 10.5, that's going to give me the perimeter of the entire place, which happens to be 56. So that's 56 feet. That's your perimeter. And then for the area, take the same thing again. You know that you're going to be able to do 17.5 and multiply it by the 10.5 because those are your original measurements. Those are the new original values. That means that the area, or sorry, not the original, those are the new scaled values. So the area is 183.75 feet squared. Or you could do 5 times 3 and then multiply it by 3.5 squared. And that would give you 183.75. Let me show that off to the side. You could do 5 times 3 and then multiply that by your scale factor of 3.5 squared. That's going to give you the same exact thing here. All right, let's take a look at the next one. All right, length of a bus and the width of a lake. A scale drawing of a school bus has a scale of 1/2 of an inch representing 5 feet. So 1/2 an inch is going to represent 5 feet. If the length of the school bus is 4.5 inches on the scale drawing, then what is the actual length of the bus? So 4.5 inches compared to 1/2 an inch. How many feet compared to 5 feet? We're setting up a proportion. So what I'm going to do is I'm going to take what my scale values are and I'm going to put them over what the actual values are. So I know that 1/2 of an inch is the same thing as 5 feet. So I want to know 4.5 inches. What's that going to represent as X feet? So you're just setting up a proportion. So then I would do my cross products to solve. I would do 1/2 times X, which comes out to 1/2 of an X. And then I would do 5 times 4.5. That's going to come out to 22.5. And then if I just divide both sides by 1/2, then I'm going to get that X is equal to 45 feet. So that would be your actual length of your bus. You can do the same thing here for the width of the lake. You have a scale that's 1 centimeter represents 80 meters. So I'll just do it in a different color. 1 centimeter to 80 meters. We want to know how many centimeters will represent 1,000 meters. You're just creating a proportion and solving where you have things that are going to match up. So X times the 80 gives me 80X. 1 times 1,000 gives me 1,000. And then I'm just going to go ahead and divide both sides by 80. And I would find out that on an actual map or scale drawing for it, then that's going to come out to a scale factor of 12.5 centimeters. Okay, so we're going to stop here because we don't have time to do the ending. Go ahead and pack up.